Hello, a great welcome to Idea Statica tutorial. Myself Jarajan P. This is tutorial number 18. Here I will demonstrate the modeling and analysis of a base plate which essentially supports two rolled steel columns. The columns are subjected to axial loads, shear and bending moment. The geometry of base plate used is shown here. The code checks are performed for three load combinations for each of the components, namely base plate, anchor bolts, and concrete. So let us start Idea Statica tutorial number 18. Please note that the links for other tutorials are provided under video description. So in tutorial 16 and 17, we discussed about rectangular and circular base plate for single supported sections. What makes this tutorial unique is that it supports multiple columns as shown here. The base plate is having a polygonal shape. And the third one is the base plate, anchor bolts and pedestal are modeled not using the standard procedure but through a different approach. Now let me quickly take you through the different operations performed to complete this model. So first let us go through the modeling of the columns. So we have the two columns here. For example, here you can see that M1. So it is HAF 450 and it's a vertical one. So we have provided a pitch angle of 90 degrees and it is a NVM connection type. Then we have the second member, that is M2 as shown here, and that is an IP360, is a smaller column size, and it is provided with a vertical angle of 90 degrees, and the orientation is maintained through an angle of 90 degrees, and it is conveniently positioned with respect to M1 at a distance of EZ is equal to 400 mm. Again, this is also an NVM connection type. Now, having modeled this M1 and M2, we are going to model directly the base plate, and in this case we'll model the base plate through what we call as the stiffening plate manufacturing operation. So SP1 is the manufacturing operation that we have performed. So let me quickly take you through. So this is our stiffening plate manufacturing operation that is used for the generation of the base plate. So as you can see, let me quickly introduce you to SP1. It is of S275 material. The base plate thickness is 35, and all the dimensions are provided. The pre-calculated dimensions are provided in the form of B1, B2, H1, and H2, and all this X, Y, Z, and the rotations are kept as 0. And here you can see that we have a rectangular base plate generated through this command, and which needs to be edited again. So what we can do is that you just press the editor and you can start providing the bevel edges as shown here through the two bevel operations as shown here. So now having modeled this base plate, we need to model both the angles as well as the foundation block through another command known as the grid of bolts. So here I will show you the grid of bolts command. So this is the bolt grid manufacturing operation. So in this case, using the bolt grid manufacturing operation, we will be able to specify both the anchor plates as well as the foundation blocks. So as you can see that we have the two items over here. So that is SP1 is one item, and then we have got the anchor bolts as M34.6 grade, and the anchor length being kept as 600 mm, and the anchors are provided with a circular washer plate of diameter 100 mm, and then we have the foundation block, and the foundation block is provided with a concrete of grade C2530 with an offset of 500 mm, and the depth of the foundation block is taken as 1000 mm. The shear transfer is assumed through the friction mechanism, and the standoff is taken as a direct. Now we need to connect the column numbers M1 and M2 to the base plate SP1 through welding, and this is being achieved through the cutoff plate command. So pcut1 if you see. So let me just see what this command is all about. It's operations. So here you will find that we have here a cutoff plate command, and this cutoff plate command in this case is used to properly specify the welder connection between the columns and the base plate. So as you can see that pcut1 command, it specifies the connection between the base plate SP1 and the member M1, and we have provided the connection through a 6 mm double-sided fillet weld. And in a similar way, we have got the pcut2 command, that's a manufacturing operation, wherein we connect the base plate SP1 with the vertical member M2 through a relatively small size, that's a 4 mm size double-sided fillet weld. Now here we have another component that is generated. As you can see, this is the component. Okay, let me just take it a little bit to this direction. Yes. So these are nothing but the wideners. Okay, the wideners are again generated here through the stiffening plate. So why these wideners were provided? It's very simple. So initially the model was generated without the wideners, and the analysis shows that a large amount of strain is getting developed in the base plate. So accordingly, to distribute the flange forces to a larger area and thereby to reduce the strain levels, we have provided the wideners, and the wideners are provided using the same stiffening plate command. So you can see that these are of S275 and the thickness is 10 mm, and all the required parameters are provided here, and we can say that it is connected to the member M1 bottom flange, and it is provided on both sides. So the connection of the wideners to the bottom flange, it is done through, you can say that here is a butt weld on. Okay, so now coming to the other operations, P-cut3, and this is the same the plain cut manufacturing operation, P-cut3 and P-cut5, and these operations are very specifically used to enable the welder connection between the widener and the base plate. So we have got SP2A and SP1, and the connection, there's a fillet connection on both sides. It is provided with a size of 5 mm. And coming to the other stiffener, other widener, we have done the same the plate cut manufacturing operation. We have enabled the welder connection between SP2B and the base plate SP1 through the both-sided welder connection, fillet welder connection of size of 5 mm. And now we have the SP3. It's the same stiffening plate, but it is provided with the top flange of the beam. So let me quickly see. So we have, yes, so it is the same widener, but it is connected to the other side of the flange. So you can see that it is of the S275, the same parameters and 10 mm thick, and these are the basic parameters. It is connected to the top flange one, and you will find that the connection of this widener to this flange, it is enabled through a butt weld connection. Now in a similar way, the connection between the widener SP3 and with the base plate, it is enabled through the plate cut manufacturing operation P-cut7 and P-cut9. So that means our model is complete in all respects. And here I just want to add one thing. In the grid of bowls, we have in fact added, if you see this, so we have added first of all the bolts that are on opposite sides of the flanges of M1, and the bolts that is relevant to the M2, that is added through the so-called, the editor command. So if you see the editor, you will find that here what we can do is we can just explode the assembly of the bolts and start specifying the locations of 11, 12 and 13 through the editor command. So now, so we have completed our model. So let me just zoom it. So you can see that this is our model. So ensure that all the components are properly connected to each other, either to the boards or the wells. That is very important. And now let me quickly take you to the various loading effects. So here the system is checked for 3 load combinations, and here you can see that LE1, it consists of basically M1 being loaded in N, V and M, and M2 is subjected to only an axial load. And LE2 on the other hand, you will find that the main member is subjected to only an axial load, whereas the member M2 it is subjected to an axial load and a moment. And in LE3, what is done is that the sign of the various force components are changed for the member M2, because as you can see that the bolts are provided only on one side. Just to check whether the connection is safe, what is done is that the force resultant that is acting on the member M2, that is reversed in LE3 combination. So that's all about the loading. So now it is important one more thing, that is here we have to go for the equilibrium check. Okay, loads in equilibrium condition. Okay, so that is already okay activated here, and now we can start calculating the model. So as you can see, our model is fully run, and let us see that analysis result. You can see that for all the three combinations, LE1, LE2, LE3, okay, the analysis is done for 100%. Now let us quickly start verifying each and every component. Now let us first start with the plates, and it is shown that plates are okay with a percentage of 0.9% strain, which is below the target value of 5%. Let us see which of the component plate is critical to us. So we'll just press okay the plastic strain distribution, and let us go straight away to the plates. So coming to here, this is your plastic strain. Okay, so let us just quickly arrange it a little bit. So we find that 9.9% strain, it comes in the plate SP1, that's the main base plate SP1, corresponding to the load combination of LE2. So here if we quickly start seeing how the distribution of the strain is, where it is critical. So this is my SP1. Okay, so here you will find that in SP1 as usual, the strains are critical. You can see that it's somewhere at this points, okay, where okay the column M2, it is connected to the base plate. At this points you'll find that it's a small, okay, so blue shade, wherein we find that the strains are to the tune of 0.9%. Now if you want to reduce the strain below 0.9%, I would advise you to add the wideness here as well. Okay, now coming to the other one, 0.7, we find that the critical ones are the my wideness. Here you can see that the wideness, so the same is shown here also. So here you find that the strains in the wideness, it has gone up to the range of 0.7%, and the same is for the other also. So in other words, we can say that the strains are critical in the widener connected to the main column M1 and also to the base plate that is directly under the flange of column M2. So that's all regarding the analysis of the plates for the strains. However, we find that the strains are 0.9% is acceptable. Now the next one is the anchors, but the anchors we will discuss a little bit afterwards, because we find that here the ratio is 153.8%. It is not meeting our requirement. Now coming to Now straight away coming to the wells, we find that it is 99.6%. That's okay for us. Now let us go to the concrete block, check for the concrete block. So before that, let us do one thing. Let us start obtaining the distribution of the bearing stress. Okay. Now you find that this is the distribution. Obviously, this is subjected to a moment like this. So it does mean that we find, okay, for the extreme case, the bearing stress is critical under the flange of the main column M1, and you find here that the distribution, okay, the bearing stress maximum has gone even up to 27.9. So let us quickly see the results provided by Idea Statica. Look here. Here it has given a check of the contact stress in concrete for the extreme load effect. So the item is here, what we have is a CB1, that's a concrete block that is being checked, and is checked for LE1. And here you find that C, that's a very important parameter that's derived as per the Eurocode, that's a bearing width. And in fact, in Eurocode, what is done is that the bearing width dimensions are computed, and the entire flange force is assumed to be distributed over this area. So here you can find that there is an effective area which is calculated by the Idea Statica. And sigma, this is what we call as the average stress in concrete. So here we find that the concept of the average stress is a little bit, confusing to us. Here we find that, in fact, the bearing stress distribution, it varies, very sharply across this bearing width. So here we find that the maximum absolute value is 27.9, but if you use this concept, the mean stress calculated is 15.5, and whereas as per the code calculated design bearing strength is of the order of 33.5. That's why we find that As far as the stress utilization is concerned, it is 46.2. But even considering the local variations in the bearing stress, we find that we have got a bearing stress to the tune of 33.5, bearing 33.5 Newton per mm square, and the actual bearing stress is only going locally maximum of 27.9. So we don't have any problem as far as the bearing stress is concerned. Now let us quickly go to one more item. I think we have yes. So here we have got the shear, and this is nothing but the shear check of the concrete considering the applied shear. So we have here given as the shear force applied of 99.6, and the computed shear resistance is of the order of 485. And accordingly, we find that as far as the shear is concerned, the utility ratio is of the only order of 20.5. That's acceptable to us. It's a very 20.5 as indicated here. Now let us go to the critical item, that's the anchors. So we have plus anchors, and here let us just start reviewing the results. So let us first see what are the actual tensile force in the bolts, maximum tensile force. So we let us just arrange it in an order. Okay, so here we find that the bolt A19 is critical, right? So here what we do is we just go for the bolt forces. So here we can have so A19. So just a minute. So we have it as so here we find this the bolt force, that is maximum 86.3. That is as expected. It is in this extreme bolt A19, and so A90. So let us see what are these bolts which are creating problem. A19, A17, this one, A15 is this bolt, and A13 is this one, and there's also one more, yes, A11 bolt, that is this one. That means all these 5 bolts which are lying in a single row is creating a problem for us, and we don't have any problems regarding this A22. Let's see A22, this bolt we don't have any problem, they're all right. 21, these bolts are okay for us. So the problem is exactly considering the row of bolts on these sides which are subjected to a large amount of tension. Now let us see what is wrong with these bolts. So coming to this, well, let us press for example the case of A19. Okay, so in A19 we find that its capacity is of the order of 95.4 considering the structural capacity of the anchor bolt, whereas the actual tension coming is only 86.3. So it does mean that considering the capacity of the structural capacity of the anchors, we don't have any problem. It does mean that it is some other factor that is playing the that is creating the problem to us. So let us do one thing. So let us just start investigating. Yes, here there is NRDC. This is a very important factor, which is normally we call it as a concrete con. So if you press here, you will find concrete con breakout resistance in tension. This is one factor which we need to investigate in detail. So here you will find that for all this, okay, for all these failed bolts A19, A70, they are marking the same thing: 290.4, 290.4, 290.4. So and 290.4. So now we need to investigate why this the con breakout resistance is the same for all these failed bolts. And here you will find the utility ratios on 2 counts. One is the utilization only in tension. So if you consider only the tension, you find that the ratio is 1.33, okay, which is greater than 1.0. And now if we consider an interaction between the tension and shear, it goes up to 1.53. But in my opinion, the problem is we assume that the entire shear will be transferred through the friction mechanism. It does mean that no shear force will be transferred to the bolts directly. So I think that this column need not be considered. So we should consider a factor of 1.33. So first of all, let us see how this ratio 1.33 is evaluated, and from this how they have evaluated 1.538 ratio. So in order to get a very good view of the calculation, let us straight away go to the reports, which will definitely help us to see what has gone with the problem with the anchors. So in the report, we will see how the calculations have been carried out for the anchors and what are the critical things. So let us quickly go through this. So we find as expected. Okay, so we have, yes, we have got 1, 2, 3, 4, 5 bolts are problematic for us, wherein the utility in the ratio in tension is 1.33 and that in combined tension and the shear is 1.538. How this is calculated is very simple. So look here. So here we'll find out, okay, as far as the anchors are concerned, it has got sufficient tension resistance. So what is creating the problem to us is, as expected, is a concrete breakout resistance. How this is computed is, it is written, this is a very important sentence, the check is performed for a group of anchors that form common tension breakout con A11, A13, 15, 17 and 19. So all these are 5 bolts. So what is done is that they have considered a envelope of the combined cons that are formed under this individual okay anchors, and they evaluated its capacity, and the capacity that is the what we call as the breakout resistance that is formed in concrete directly below these anchors is 290.4, whereas the sum of the tensions, okay, that is under these bolts comes out to be 386.9. So this is 386.9 divided by 2.9, that's 290.4, is the so-called factor that we are having, that is of the order of 1 point. You'll find that this is 1.33. Now if you go further into the calculation details, you find one more thing, that is here they have checked the interaction of a tension and the shear forces. So as I already told you, we assumed the shear force transfer through the friction mechanism. So accordingly, the shear in the anchor, it is a 0 here. So I feel that this check we can straight away avoid, though it is kept as a check to be okay followed for the combined interaction between tension and shear as stated in easy 2. So here, though our ratio comes out to be 1.33, we are not presently not considering 1.53, 1.33. One thing is very important in the computation of this conical breakout resistance. We are considering only the plain concrete, but we are very much aware that our pedestal will always reinforced with some vertical bars, and all these vertical peripheral bars can provide a significant amount of okay resistance of concrete in breakout resistance. And still, if these values would have been very high, we have got some other alternative means of providing individual reinforcement, bent reinforcement clips around these anchor bolts in order to see that the anchors are safe in the breakout failure mode. So that's all about the review of the results. So I would request you, all of you, to subscribe my channel, because we are going to upload a lot many interesting problems in future. So as and when these are uploaded, you will be immediately notified. Okay, so that's all. So thanks a lot and have a nice day.